Okay, let's practice a little more with another example here. This is going to be the example of a very highly simplified dovetail slide. Okay. Dovetail slides are one of many different types of linear bearings that exist, and these ones are particularly useful because they have a very high surface area. So they tend to be stronger. You find them in certain machine tools. They're not intended, for very high rate, high speed, high cycle type of applications, but rather when you need a lot of stiffness. So let's say that this is the assembly that we're seeking. It's a little bit inverted, relative to the picture that I just showed you, but let's say that the one with the copper tone in there is the stationary part, then this is going to be the moving component. And we've added, for good measuring here, a plug that is meant to remain stationary and clocked in that particular way. Here are the individual part files. So this is what we call the base. Again, nothing special about it. We'll come here, look at the slider. And finally, look at the plug. Okay. Let's now proceed to put this into an assembly. Now it should stand to reason that we will want to now start a new assembly and begin by bringing in the base. As we have alluded to before, we'll want to go ahead and click the green check mark in there so as to line up the coordinate system of the base part with the coordinate system of the assembly system. That way, any manner in which we've taken advantage of symmetry or alignment, with a particular axis for the base part, will be transferred over to the assembly at large. Right, our next order of business is going to be to insert the next part, so that will be the slider. Now the second part, we can just go ahead and click it anywhere and drop it. Now, of course, there's no need, for that part to be oriented at the part level in any particular way relative to its mating components. We're going to do that through the process of declaring assembly constraints. Now we can see that in this particular case, it's the bottom surface of the slider that we're going to want to mate to this inner top surface of the base. So now in this case, again, I'm going to hold the shift key, select both surfaces, select mate, or I could just come here and even accept just the default, coincident. Now, of course, when we talk about coincident in there, just to clarify a little bit of the terminology, so coincident, if we're talking about coincident points, okay, that's one point literally on top of another. When we talk about coincidence, in the context of lines or edges, that just means collinear. Collinearity doesn't imply that one starts at the same point as the other. It simply means that they lie along the same line. And similarly, coincidence for planes, coincidence for surfaces implies coplanarity. So again, no description of the relative position to one another other than the fact that they lie on the same plane. Okay, so when we do this, when we enforce that mate, we will see that as usual, certain number of degrees of freedom have been removed from the part. Okay, so in this particular case, we see that the part is free to move in the Z and X directions, but it's no longer free to move in Y. Now, it may look like it's moving vertically, but don't be fooled by that. If you look at a front view of this part, there is in fact no way that I can push it up. I can certainly move it sideways this way, and similarly, if I look at it here from the side, I can certainly move it sideways this way as well. Okay, so just make sure you're not taken aback, by visual effects. All that's happened here is that these two parts became farther apart. Okay, so this speaks, of course, to the need of enforcing a set of additional constraints in order to be able to have our assembly as we intend. So probably the next order of business for these parts would be to enforce a constraint that would keep the slider in the middle of the base. Okay, even if we were okay with this part, not being restricted at all along the slide, at the very minimum, we certainly don't want it to go sideways. How would we do that? Well, different ways. Okay, we could, for example, enforce a distance between this face in here and that face there. Okay, so that would be this particular constraint, and we could figure out exactly what that distance has to be in order for the slide to be or to go right down the middle. So let's say that we knew that that was 4.5 inches. Okay, so you see that it moved a little bit. Obviously it isn't. Let's try 4.1 and see if we can do any better. Okay, perhaps 4 on the dot. And there we seem to be getting closer. Okay, now if I just left it like this, now I have restricted in the slider the ability to move sideways. It can only move along this way, so it seems like we're making progress, but clearly there's still some issue there. We're not quite centered perfectly, are we? Okay, so if we were to look at a front view, okay, we can see that we can no longer move it sideways, we can no longer move it up and down. So that's all good news, but we're not quite centered. Okay. Now, in some cases, we will know exactly what that distance is, and we can apply that constraint. It seems like a stronger way of applying that constraint is not by the application of a dimension, but rather by the enforcement of a geometry. Okay, so what would make sense to cover something like this? Let's first of all go ahead and delete this constraint. Okay, so now we're back to being able to move this in multiple directions sideways. And what I'm going to suggest here as the next step is that we simply take advantage of reference geometry. So we'll go back to this part in here and make sure that we have a plane that runs right through the middle of it, similarly with the base, and then we can align their respective reference geometry. Now, from any assembly, we can right-click on a part, and here in this menu, we can open that part. We can open the source file that created that part. I'm just going to go to reference geometry, create a plane by selecting that face and this face. Now, as we know from reference geometry, that will create a plane that runs right the middle of those two. So we'll just click OK there, and then close, save the part. SolidWorks knows that that part is being used in an assembly, and it's asking us if we want to rebuild the assembly with those changes, which we do. So now this slider has a new plane in it, that didn't exist before, and this plane rides right down the middle of the part. So all we really need to do now is apply that same situation here to the base part. Now let's look at the base part, see how it is aligned. Okay, and we see that this base part, appears to have been designed already with some symmetry in mind. Okay, so in fact, if we expand this tree and we highlight both of those planes, okay, so the right plane for the base and this new plane here for the slider, and now we look at a front view and turn on all the planes. Okay. We'll see here now that if we manage to align these two planes, then the dovetail slider will be exactly symmetrical. So let's go ahead and do that. We'll select here the right plane, hold the Shift key, select that plane 1, new plane that we created for that part, and then make them coincident, which is to say coplanar. And the process of doing that, if you noticed, led the slider to move slightly to the right. And now if we look at a front view, we'll see that things are exactly where they need to be. Okay, so this was a geometrical constraint. Notice that the constraint didn't have to apply to a feature of the part. The constraint was perfectly workable using reference geometry for that part. Okay, and then finally notice that we didn't have to rely on dimensions. Now, in the process of building these parts, we know what dimension would have cost that dovetail slider, to run right down the middle. Okay, but this, I would argue, is a stronger, a more purposeful, a more direct way of embodying the design intent, which is, of course, you intend for this to ride down the middle. Now, of course, as we look at the fronting here, there's some gaps. Well, those gaps are arbitrary, and they amount to the clearance that there would have to be between those surfaces in order for this part to be actually assemblable and to be able to have relative motion. Pay no heed to what those distances are right now. We will have plenty of chance to talk about in future lectures. Okay, so it looks like we're now in fairly good shape. Okay, let me go ahead and turn off visibility to the planes. In fairly good shape. We can move this the way we want to. It's restricted to the single axis. It's nicely centered. we might want to enforce a limit of displacement in there. So let's see how we can do that. Let's go to mates and find out, what we have. So first of all, we have standard mates. These tend to be just the common geometrical mates: coincidence, parallel, perpendicularity, tangency, and then distances. Okay. All right. Now we also have what are known as advanced mates. Okay. These advanced mates come in different flavors. One of the more useful ones in here is width. So in fact, width would have allowed us to do the exact same process that we did before, but in even fewer steps. Instead of having to create intermediate reference geometry and then align those planes of symmetry in there for the dovetail and the base, we could have just selected the outer edges of the base, the outer edges of the tail, and declared a width constraint, and that would have aligned them naturally. Try it. You can find out it's very, very useful when you have to align things where there's a gap there in between. Another extremely useful mate in here is the distance. Now this in here should be really known as limit distance. This is what allows us to impose a dimensional constraint, a dimensional limit for a constraint that would otherwise be infinite as in an infinite plane and an infinite line. Okay, so let's put that to use in here and enforce a limit for this slider. Okay, so let's say that what we want to do is limit the distance that this face in here in the slider and this face here in the base are ever going to experience. Okay, so we select the two of them, and then we come here, go to the limit distance command, and we can specify a minimum and a maximum. Okay, just as simple as that. So let's say minimum value of 0, meaning that they would be coincident, and then let's say a maximum value of, well, let's say just round it up to 3 inches, and we'll go ahead, accept the mate, and see what effect that has. Okay, notice that now if I try to move the slider, it's going to stop when that minimum distance of 0 is reached, and it's also going to stop rather when that maximum distance of 3 inches is found. This can be applied for both linear distances and angular distances, so very useful indeed. And again, remember that as we have added all these mates, they have all become available here under the tree. Remember that these are self-standing entities. Within the feature tree, they can be edited, they can be deleted, they can be suppressed, and just generally dealt with in any manner in which any other component in the feature tree can be manipulated. You can also see the mates on an individual part basis. So if you go, for example, open this particular part, you can see what mates are available for that part. Okay, so it says there are mates in assembly 4 in there, so you can see all the mates that apply to this part. Of course, in this case, the mates are going to be the same, since all the mates are between those particular components. Okay, let's finish up this review of mates in here, or at least the non-mechanical mates, by bringing in the plug, which we haven't talked about. So we'll come here to insert components, bring in the plug in there, and by now you can guess this is just a simple matter of selecting that surface, this surface. Okay, concentricity, that would do it. Okay, so that's good for one. We can add another mate in here, the bottom side and the top side, and make those coincident, which is of course the default. And then finally, to clock that hex plug, and not that this would necessarily make any sense in real life, but just to complete the example, we might select this surface and this surface. Okay, now notice in here you don't want coincidence, because coincidence is impossible. There's no way that we can make these two surfaces coplanar, given all the other mates that we have enforced. However, we can apply a parallelism constraint, and that will be just fine. But just to make this point, let me purposefully choose coincidence there, and notice that the mate command is going to give me an error. It's saying the components cannot be moved to a position which satisfies this mate. Okay, but that can be relaxed simply by selecting parallelism, and that will do the trick. All right, we'll finish up our very quick overview of mates, taking a look at mechanical mates, and then we'll call it good for this section. As usual, you will have plenty of opportunity to practice this on your own and make it yours.